Hey folks, welcome back to session 3 of day 2 of Social Networks in Health. I'm really pleased to have Peter Mucha here with us. Peter is a longtime friend of the family, if you will, and he has abandoned us and moved to the great Northeast. But other than that, he's a great person. And so, no, I'm just busting him. But anyway, it really is great for Peter to have here. He's been working on this question of partitioning and graph community detection for a long time, and I think has made some really remarkable advances in it. So thanks for joining us, Peter, and the floor is yours.
Well, thank you very much for having me. Not knowing, how much people wanting to sort of balance people who didn't have a chance to look at any of the materials that are posted, while also making this useful for the people who maybe did and want to get to some questions. I just thought I'd do a super quick overview here of some of the thoughts that I tried to present in the materials. Let's see here. Hopefully, can you now see that screen? Yes. Okay, good. All right. So you see a title slide. Good. So I just kind of wanted to do a quick overview of some of the things that I think about when I think about community detection, because I think it sort of permeates the philosophy that runs through the document in my previous lectures. Thank you again, though, to Jim and his whole team, while I say previous lectures, for the number of times that they keep having me come back with, whatever the little updated tweaks are. It can be a little confusing if you go back through some of the lectures, because the available tools that you have in R to do community detection have changed in wonderful ways since I did one of these lectures. However, 2017, 2019 involved a crazy thing with Python and Reticulate. 2021 involved all sorts of things. If you go through the 2021 lectures, there's a big section about having to use the development branch of iGraph. I am thrilled to say you don't have to do any of that anymore. You get to just start doing things, and now we get to focus on bringing better tools. But here's sort of my quick intro to why one of the reasons, as an example, that I think community detection is super cool. So this hairball here is a force-directed visualization of a very small corner of Facebook from the fall of 2005. So this represents, this is actually 2005. You go back that far in Facebook, right? You needed to have a .edu address to even be on Facebook. So this is what Caltech .edu looked like on Facebook on a particular day in 2005. And so the usual bit, we're all used to what Facebook is now, but just to maybe orient us, this hairball here, every node is somebody's Facebook account, and the edges between them are the indicated Facebook friendships, which of course have been declared to be reciprocated. By itself, the force-directed layout here maybe wouldn't be terribly enlightening, but I've already kind of nudged us towards what part of my story is going to be, because I've colored and shaped the nodes here according to a particular node attribute. The node attribute in this case is the house information volunteered by users on their profiles. House at Caltech is something that's very loosely, apologies to anybody who actually knows or has lived it, it's something loosely crossed between dorms and Greek life. Basically, everybody sort of self-sorts when they arrive first year. They join houses. Almost everyone stays in the same house for their whole 4 years. So you would expect, and the hypothesis going in here was that, in fact, the house information, the house affiliation would have a big influence on the social life at Caltech. And so, if you squint in the right way, you can sort of see some of the colors and shapes grouping together, or you get very hungry because you're thinking of Lucky Charms. Community detection basically is just unsupervised clustering of objects in your network, typically nodes, that can then be used to identify patterns directly from the network connectivity. So this picture is exactly the same data, having been processed through just one choice of a community detection algorithm to give every node a community label. And so every one of the pie charts here represents one of the algorithmically identified communities. And importantly here, we found these communities only from the network structure, not using any of the node attributes in this case. But then the colors are the house attribute. And so you can see that there's a really strong alignment here between the house affiliations and these algorithmically identified communities. You have this Pac-Man looking pie chart in the middle of the image, yellow eating a purple wedge. Most of these pie charts are heavily dominated by one color, that is a majority, in some cases an overwhelming majority of the people in that algorithmically identified community are from the same house. At the top, near the top of the figure, you have sort of the red and the cyan community. Those happen to be two houses right next door to each other on one end of campus. So, I mean, it makes sense, right? It's a tool clustering your data, just like, we do with any clustering tool, to group our, to sort of see what the clustering is of our data and then see if that aligns with something else that we might know about the data set here. Of course, the one outlier color is purple. Here you can see purple sort of scattered across these many communities. Well, purple is the users who didn't tell us on their Facebook pages what house they were affiliated with. But, if I were a betting man, I'm going to take that purple wedge being eaten by the yellow Pac-Man and think that pretty much the vast majority of those are in the yellow house. That's just like one quick sort of how you might use community detection story. And I think what I want to say here with this really brief overview conversation are just to make sure that I deliver these takeaways for you while you're looking at my files or looking at my old lectures or thinking about what questions you might have. First, to orient you in the old files, if I hopefully you can see my browser now on the DNAC training page, right? Good. Okay, just making sure that it did that. Right. If you go down and you and you click on the community detection files, there is this important note here, right? That the most up-to-date file is the one, of course, titled with a 2022 in it. The design choice I made for this year was I decided that even though there's that whole development branch piece of the story in 2021, apart from that, most of the lectures from last year I think are still pretty good. But I wanted to update them with this new document and this new R notebook for 2022. I really intended to be something that would stand alone. So big thanks to, if we click on that, big thanks in particular to Ava Sharfstein, who's an undergrad here at Dartmouth, went through my old notebook and tried to point out lots of places where I wasn't being clear. So there's probably more text in this notebook now than there is actually code. Hopefully it's a good standalone. Anything that's still missing is my fault, not Ava's. She tried to get me to put even more in. I do not mind if you reach out to me and ask for clarification about anything that happens in here. In fact, I'd welcome it because it would really help us continue to develop these tools and help you use the available tools in the best ways that you can. So, second is maybe this point that I already started to make is to just, there's been a lot written about community detection over the last 2 decades that maybe is just kind of wrong about magic of identifying how many communities we should identify in your network or how big those communities should be. And I think really the safest and from a data science perspective, most intellectually honest way to think about community detection is to just see that the many different tools for community detection are completely akin to the many different tools that exist for unsupervised clustering of point cloud data. There's no one right way to cluster data, and there's no one single right way in all cases to cluster your nodes into communities. There are many different tools. Many of the tools have knobs on them. A lot of what I do in this notebook tries to emphasize how to turn the knobs that now exist finally in a more easy to use way in our iGraph in a positive way to explore your data. Because ultimately, right, that's what we're doing in unsupervised clustering of data. It's an exploration tool. It's not necessarily by itself explanatory. What a group or a cluster or a community or whatever you choose to call it, whatever it actually means for your data, undoubtedly depends on the application and depends on how you went about finding the communities. So in this Facebook example, right, there's a hypothesis going in. We write a lot more than just what I showed in those quick pictures about, how the Caltech Facebook data is different than other college data in a way that highlights this house affiliation as being important. But just think about community detection as a tool, not as an endpoint in and of itself. And then the last big takeaway message that I want to make sure that I say loud and clear here is that there are still methods that are not yet available in R. We're transitioning some of these that exist from Python over into R as part of the IdeaNet project that Jim did an excellent intro on yesterday. So keep watching, and there will hopefully be more things. And if Jim's nice enough to invite me back again next year, then maybe we'll have more of these tools for next year. The notebook spends a lot of time on the Zachary Karate Club because that's effectively an obligatory thing to look at whenever you're talking about community detection. It's a great story, right? I go into it a little bit in the notebook, but basically it's very well clustered data. If your method doesn't work on this data, then go home, which is effectively what Eric Kalakshik said at a conference that we had about a year ago when he got sick and tired of seeing people do community detection on this network because it was just so overused. This particular visualization here is actually showing the optimized partition of nodes into 4 communities separated by the dashed lines, and seeing that it aligns well with the faction attribute that you will find if you load the karate data into R, which represents the 2 subclubs, 2 new clubs that were created when this club got into a disagreement between the president and the lead instructor. And so you can see that there's a very good alignment here between these 4 communities and these 2 factions. But this is very well clustered data. Almost anything that you do on this data is going to find a partition like this. Which is again, because really it's just various tools for unsupervised clustering of data. And that particular split was using what is called modularity at its default resolutions. Pretty much all of my notebook is focused on ways to access modularity, but ways to do it at beyond just the default resolution. That's important because modularity is problematic. It's a purely descriptive measure being used as an objective function to be optimized. It's not statistically principled in any generative sense. It only finds assortative structures. It's biased towards balanced communities. There's all sorts of issues with it. It is nevertheless the most used method of community detection because it's right there. It's easy to access in a lot of situations. The heuristics that exist are very fast. Because of this, it's also very frequently misused. And a lot of my notebook is, if you like, trying to coach all of us to use the tools that already exist in R in a more intelligent way to explore our data. And so a lot of the notebook is about how do we go about picking the so-called resolution parameter, which is typically written as gamma. When you go to multi-layer networks, then you just even have another parameter, and we don't even touch multi-layer networks right now in the at all in R, and that really needs to be one of the things that gets developed better going forward is community detection for multi-layer networks. There are some packages that are available, but they're not as straightforward to use. And so our overarching philosophy here in putting together this notebook and giving this quick overview talk is basically to say that, if you're going to use modularity, we want to help you use it right. This is the typical thing that has been available to people so far is something like this. You load your data, you call a function, it splits your data up into groups, you plot some things, you're done, you go home. That sometimes will work. And there are cases where if you learn something interesting there, that will work. But the notebook spends a lot of time dealing with the fact that there is a resolution parameter in the modularity framework. The default is that it's 1. this gamma parameter, and basically we're trying to help show ways in which you can use it in a more intelligent manner. If I can get to just maybe one more slide here to show you, is a screenshot out of the notebook. One of the examples we use is this American College Football Network. It's one season back from what used to then be called Division 1A college football. It's a data set put together by Mark Newman. And the particularly interesting thing about this picture here, what we're plotting is a very simple diagnostic. And again, this is right in the notebook, of the number of communities that are being identified at different values of gamma as we sweep over this data. And the really important takeaway here of this data, right, is that the default, which is gamma equals 1, is on this, what I might think of as a sort of a very noisy ramp up in the number of communities being identified. It's not very stable. You tweak gamma a little bit smaller than 1, a little bit bigger than 1, you're going to get very different results. But there's this big plateau in the middle, where above 1, where for a very long range of gamma, you get the same 12 community split of these college football teams into communities. And it's very well aligned with the conference structure. It makes a lot of sense that would be a very robust split. This is tuning gamma like this, is letting the data try to tell you where the meaningful scale is in the data, and it works out, I think, really well here in this example. There are a lot of other tools that we hope to expand upon in coming years, but I'll just leave a couple of the links here for you. They're also in the notebook. And thank you for your attention, and I'll use whatever time we got left to see if there are any questions.
Awesome. Thanks, Peter. Really appreciate it. Floor is open for folks to jump in with questions. Just as a warm up while people are forming their questions, do you have any praise or shade to throw on non-modularity methods that are your best preferred, least liked, any of that kind of thing?
Neither praise nor shame. I think there've been a lot of fights in the community, the intellectual community, about my method's better than your method, etc. At the end of the day, right, I really think the right way to think about this is it's completely akin to the many different ways that you might cluster point cloud data, right? You might have Gaussian mixture models, and you might have k-means data, a k-means algorithm, and you might have, some other unsupervised clustering method, and no one of them is the quote unquote right way to do it in all cases. Having more tools is better, trying out different tools, seeing what the options are in those tools under the hood, and really using it to explore your data, I think is the intellectually consistent thing to do, because there's no silver bullet free lunch here that is always the right thing to do.
Yeah, I think that I would, obviously there's some network autocorrelation here, but I think one of the things to point out is you really do want to spend this time doing the exploration, and this is reiterating the point we made yesterday in the first session, which is to visualization and exploration and other kinds of bits are really, really important. So
right.
I see Fenji Zen has a question. Why the community detection is unsupervised?
Right, that's a great question. There are some semi-supervised methods for community detection where if you force labels onto some subset of your nodes, can you use those labels on a subset of your nodes to learn the labels on others? Yeah, I didn't touch on any of those, but I know Fenji, so we can also talk more about this if we want. Well, I can also talk with people who don't know me. That wasn't that wasn't discouraging. I mean, I guarantee you will find multiple papers if you just look up semi-supervised community detection.
Gotcha. And so just I hadn't heard that term before, so this is a new one for me. So it's kind of like saying we know this person is a Democrat and this person is a Republican, but we don't know who these are. Who they go to best? That's the model.
Things like that, yeah.
Okay.
Yeah, exactly.
Okay.
I actually had a very similar question, but I have a different question. Is that you focused, as you said, like in your R script and then here on a lot on tweaking the modularity within a specific community detection strategy. What could you talk us through a little bit of what's the right way of comparing across the different community detection strategies? And there is like an innumerable amount of them, but it seems like there's maybe a right way to pick 6 to 9 and look through varying results. And the issue I've run into before is like, I'm not quite sure that the gamma for one strategy is comparable to the gamma to another necessarily. Maybe that's the case, but I've never quite been clear on it. And so what if I wanted
to... That's a great question in particular, since, right, I mean, a definite shortcoming of the notebook document that I put together is that it is highly focused on just one R code, the new cluster Leiden code that was only released in iGraph 127, which I think was like last October. And that's why we were all downloading the development branch at this workshop a year ago, which, as painful as that was better than trying to get R to talk to Python. The reason for the focus on cluster Leiden is pragmatic, because it is really the piece of code that I know of in R that even makes it easy to tweak the resolution parameter at all. I think the only other one is the cluster spin glass code.
Spin glass has gamma, yeah.
Yeah, so spin glass has gamma. Spin glass though is like a slow simulated annealing. Like, I mean, it's an intellectually beautiful idea, but it's a really slow computational heuristic. And so I think it doesn't particularly scale well to larger networks. Then sorry, I saw the chat, so I stopped myself from my own sentence. Yeah, I mean, I think, these other codes definitely have, walk trap is one in particular that I've seen lots of people have great success with in smaller networks, because it's a little more involved with regards to probing. Did you really get the optimization right? A lot of actually what we try to do in what we call our champ code, which really we had better bring to R in the next year as part of the IdeaNet project. The beautiful thing to me about champ is that it's completely agnostic to how you found communities to begin with. It's a post processor that says, I'm going to take all comers and work within a modularity framework and tell you which of all of your input sets of partitions of nodes but into different communities wins at different values of gamma. So it then doesn't matter whether you got them from cluster Leiden, or you got them from walk trap, or you got them from spin glass, or you just put them down by hand because you thought this was a good cluster. It will synthesize those results across all of them. But yeah, that's why the notebook's very focused on gamma. I mean, on cluster Leiden is sort of just out of functional necessity. I see that there's some questions about multi-layer networks. Yeah, so there's a lot that still I think could be. Yeah, so this was the asterisk when I said things not yet available in R. There are some packages that have become available, like multinet, for doing some kinds of multi-layer network analysis in R. I think there's still a lot more that can be done with those tools and to make them talk better to some other tools. MuxViz does a really good job of connecting into some iGraph data, for instance, as one possibility to use. For community detection, the available tools to do multi-layer modularity, I think, are still pretty limited. And there are again some, there are other ways to do multi-layer stochastic, various variants of multi-layer stochastic block models and things like that we hope to bring, as part of the IdeaNet package into a more cohesive framework. And then lastly, the benchmarks for testing multi-layer network community detection. There are some benchmarks. Mason Porter and some of his students have developed some different benchmarks for multi-layer community detection, where they've used some. There's a paper by Ghassemian and collaborators. I'll go stick those in the chat after I'm done with my. I'll stick the links in the chat, and if you log out and don't see them, feel free to email me. I can help you find those.
Awesome. Thank you very much, Peter. Really appreciate it. And I encourage everyone to go check out that notebook. And if you're going to spend any time doing community detection, the joke in my house is when my wife asks me what I'm doing, I'm finding groups. So there's a lot of time spent as a network analyst that we spend doing this kind of work. It really is fundamental to especially for social scientists, because the community that people are nested in is so much more, than just your ego network, and this gets you at that meso level in a way that's really important. So, yes, there's a lot here to be done, and if you're going to get, if you're going to drink this Kool-Aid, you're going to find yourself spending a lot of time here. So,
exactly.
All right, great. Thanks again, Peter.
Thanks for having me.
A little bit now, and jump into some applied actual health elements. Dana, I'm going to go ahead and stop the recording and start it again, just so that people can come and go as they see that. Stop that.